Okay, so on this question, we are looking at, it says all, make this bigger for you. So are phone calls equally likely to occur any day of the week? The day of the week for each of 553 randomly selected phone calls was observed. The results are displayed in the table below using alpha 0.1 significance level. So in other words, like this might be like a hospital or a police station or something like that, emergency services. Do they get the same number of phone calls like every day of the week? Probably not. There's probably more police and ambulance calls on the weekends, right? Saturday and Sunday. People do crimes, people, get hurt more than Monday through Friday, I think. Anyway, so how do you test if a bunch of things are all the same? That's really the question, right? It says, are phone calls equally likely to occur? So it's an equally, let me just write that for emphasis, equally likely, meaning all the same every day. So we're saying is every day, Monday through Sunday, equally likely, all the same? Now you might think, well, look at this. Here's our, obviously not. 91's not the same as 68. Well, careful, remember there's always luck. And so, we're wondering like if this is a police station and we surveyed it one week and said, well, look, we got more calls on Sunday than Monday. Well, that might have been just a weird lucky week. Maybe on average, if we kept doing it week after week after week after week, we'd see that they all kind of equal out, Maybe this was a weird week or maybe not. That's always what we do with the statistics calculator, is it tells us what the chances are that we just got a random weird week, or no, this isn't random weird. It's telling us these days are not really going to be the same in the long run. That's what we got to figure out, right? Does this survey, which clearly these are not all the same, but are they close enough to the same to where we think, hey, yeah, that probably in general, they're all the same. And the fact they aren't exactly the same in this week's survey is just because of randomness, or no, they're so different. That can't just be randomness. They must really get more calls on Friday than Wednesday. They're not all the same. It's like, yeah, it looks like it's like double almost. So I think to me, they look pretty different. I mean, right, like 103 is way more than 68 or 69 or 62. Right? This is almost double, time and a half at least. More, yeah. So that looks so different. I can't believe that really in the long run, Thursday and Friday are the same, and this was just a weird week. I don't think so. Look how much more was on Friday. Way more. So anyway, that's what the calculator is going to tell us. What kind of study is this? That's probably the first tricky thing. Now you see the answer here is goodness of fit, but how would you know that? If you didn't see the answer there already. Well, let's go to the notes and take a look. So I'm going to go to the notebook, which is right there. Yeah. So I guess it's all about, if you look at the different types of studies here, see how it says equal distribution or same frequencies? That's us. That's what we're wondering. Are Sunday through Saturday, I mean, are they all equal? Same. That's a goodness of fit test. In other words, how does this survey fit with all of them being equal distribution, every day the same frequency? That's how we know, oh, it's a goodness of fit. If you're testing to see if a whole bunch of things are all equal, same frequency, same distribution, you're doing a goodness of fit test. So this is the notes. This is the unit. If you're wondering where this is the unit for notes I'm looking at. Unit 4 notes. This is number 5 on the unit 4 notes. And it's saying, look, if you've got equal distribution, all the same, that's goodness of fit. So go, okay. So that's what we got to do. We got to do goodness of fit. So that's why we come up here to the problem and we choose goodness of fit. Now, what's the HO and what's the H1? Let's go down and see. HO, observed and expected fit well or same or uniform. H1, observed and expected not fit well or not the same. So look, same, not same. That's us. There's different ways this question can come. So for us, we're going to be about same, not the same. So HO is same, H1 is not the same. Same, not same. HO, H1, same, not same. So for us, where does it say that? Oh, I guess it's uniform. Uniform means same, right? Uniforms make everybody look the same. Uniforms, same. And yeah, uniform, that's the answer. And then H1 is not uniform, which is right there, not uniform. Not the same, right? If things are not uniform means one form. So if they're not uniform, they're not the same. So that's HO. HO is same. H1 is not same, or it's HO is uniform, not uniform. So again, that was in the words. If you look down here, see how it said it. HO right there says uniform, not uniform for HO and H1. Okay, so what are we going to do? How are we going to go about doing this test? We're going to copy and paste the observed data values, and then we're going to calculate the expected data values in one of these two ways. So first off, copy and paste the observed data values. Let's go grab them. Let's copy and paste them. Come back here. I'm going to copy. Oh, wait, we've got to go to the goodness of fit calculator first off. Goodness of fit is number 21. Here I'm on the calculator page, number 21. Go to goodness of fit. There we go. So observed, let's go copy and paste the observed data values. I think it's up here. Here it is. Okay, let's copy and paste those. So I'm going to copy them. And paste them. Stick commas between them, as you know. Don't need to fix the spacing, but you do need to put commas between them. So you just copy and paste the observed database. That's what we observed. When we did our week of study at the police station, there's the number of phone calls that came in Sunday, Monday, Tuesday, all the way through Saturday. That's what we observed. Now, what did we expect to happen? That's where we're going next. How do we figure out the expected? We'll come back down here again to the notes. Again, copy and paste the observed data values. We just did that. Calculate the expected values in one of these two ways. If you have equal distribution or same frequency, that's us. Every value is equal to the total of all values divided by the number of categories. Expected equals list this value repeated, same number for every category, like 17, 17, 17, 17. So every value is the same, right? Because that's what we're saying. We were expecting that maybe all the days had the same number of phone calls. And how do you figure out how many that would be? Total of all values divided by number of categories. So we go, oh, okay. So come in here and we go, so our expected, let's do it right over here. Our expected will be the total of all values divided by the number of categories. So in other words, you have to total all these values. Like, what do these all add up to be? At least, well, it says it right here. Boom. We don't have to add them up because it says it's up. 553. So there's 553 total phone calls that came in that week, divided by how many categories? 7, because there's seven days, right? And so then just go to the calculator, 553 divided by 7. You know, you can go to the scientific calculator here at the bottom. 553, oops, I didn't do that very well. 553 divided by 7, enter, 79. 79, see it right there? So that means each one of these, remember it's the same number every time, is 79. Now how many of them? 7 of them, right? One for each day. 5, 6, I think that's 7, is it? 1, 2, 3, 4. Yeah, there it is. Because that's what we're expected to happen. If really they were getting the same number of phone calls every day at that police station, Sunday through Saturday, then they would all be the same. And they'd all be 79 because that would produce the right total. So you just list them all the way. That's what we expect to happen if they're really getting all the same number of phone calls every day. Now what the calculator is going to tell us is how well the observed fits with the expected. Like we expected them to all be the same, all be 79. In reality, they weren't. They were different, and we think pretty different. The calculator is going to tell us how different. Now just hit calculate. Calculate, there's the chi-squared number and the p-value. So the chi is that x squared number. It's called chi. It's a Greek thing, whatever. But we just do, excuse my dog there. in the middle of this. And so we're gonna go on with this problem. I hope that's not distracting you too bad. Anyway, so let's go on back. So we got that p-value, that chi-squared value. Let's take those on back to the problem, and let's see if we get those right. Yeah, there's the x squared number. Let me use this right here. There's that we said, and the p-value 0072, just like we said. So we got those two numbers. Now it's time to draw our conclusion. So the p-value, that 0072, how does that compare to the alpha level? What was the alpha level on this one? I don't know, where was it? Oh, it's right up here, hidden by my underlining, 0.1. So the alpha was 0.1. Let's come on down with the 0.1. My thing is kind of freezing up here. There we go. 0.1. So how does that compare? Well, now if you're not sure, put them over here, 0.1 and 0.0072. Yeah, that one's much greater. It goes this way, right? Because that one, you could add zeros to the back, that helps you compare. See, that one's like 1,000 compared to 0072, right? Just see how I line up the decimals? Put decimal right over decimal, and then just fill in the digits. Any blanks, just put in zeros, and then it's easier to compare. How does 1,000 compare to 72? Clearly 1,000 is bigger. So 0.1 is bigger than 0.0072. All right, so that means what? Well, that means, remember how we do our saying, if the P is low, then the HO, which is the null, must go, meaning go away, right? So is our p-value low? Is our p-value low? Yeah, it's less. See, the p-value, 0072, is low. It's less than the alpha. So our p-value is low, so that means the HO must go away, which means what? Which means we're going to reject the HO. The HO must go away, reject the HO, which means we're going to, let me see if I can put this over here. We're going to keep the H1. If we're rejecting the HO, then we're keeping the H1. And that'll tell us the rest of our conclusion. What do I mean? Well, if we come back up here now and say, okay, remember HO is always, in any hypothesis, HO is always weak evidence, and H1 is always strong evidence. So in our case, do we have weak evidence or strong evidence? Well, we're keeping H1. So that means we're going to go on back and we're going to circle and believe exactly what H1 says, which says what? Strong evidence, and not the same or not uniform. Not the same, not uniform. In other words, we're saying here it is. So we reject the null. We already said that, right? Reject the HO. Okay, now, is it sufficient evidence or insufficient? Well, it's strong. So that's strong is the same as sufficient. Sufficient means enough, right? If you study sufficiently to do well in the exam, you studied enough. Sufficient means enough. So let's get rid of all these ones that say insufficient. They're not right. It's one, but there's still three left, that say sufficient. Which one is it? Well, what are we going to include? There's sufficient to conclude that the distribution of phone calls is uniform. Yeah. Oh, wait, no, not uniform. My mistake. Not that one. Independent? No. Not uniform. There we go. Boom. There's our answer. Sufficient evidence of the distribution not uniform. Right. Not uniform. There we go. We drew a conclusion, and we concluded in the end that there was strong evidence that the days of the week are not all the same. It's not uniform. It's not all just one number all the way. It's not the same number of calls every day. And we thought that going in, because 62 came out so much lower than 103. We're thinking, no way that's just luck. No way that's just luck. You might say, well, it's just a weird week, Normally Thursday and Friday are all the same. No way. Thursday is like way lower than Friday, not just a couple lower. There's no way that can be luck. That must mean that Friday is always higher. and that they're not all the same. And that's, in fact, what the evidence told us. In fact, it gave us a p-value of 0.072. Remember, that's the probability of luck. So the chance that that was just a weird week and a lucky sample is very small, 0.072, less than 1% chance, really low that you would get that by random luck. No, that must mean the days of the week are really not all the same. So we say that's strong evidence, sufficient evidence to conclude that the days of the week are not all the same. They're not uniform. So that's how we do that kind of test. Again, how do we make that conclusion? Because we said if the p is low, the null must go. And our p-value was less. 0.072 is less than 0.01. So it was low, then the null must go, which means reject the null. If you're rejecting the null, you're keeping the other, then keep H1. Went back to H1 and just took what it said. What did it say? Strong, because remember, HO is always weak, H1 is always strong. Evidence that they're not the same, that they're not uniform. And so there we go.